Leonardo Mihalcea, who will speak about the positivity in quantum K-theory of Grassmannians.
Thank you very much. First of all, thank you to the organizers for giving me the opportunity to speak here. It's a pleasure to visit Japan again and meet some of my collaborators here. So I'm going to talk about positivity in quantum K-theory of Grassmannians, and I'm going to start by apologizing that this is a conference on integrable systems. And so the words elliptic and the words integrable systems will be mentioned, but extremely briefly, and you might miss them. So the type of positivity I'm going to talk about, so far it did not arrive from integrable system point of view, although I should say that very recently in work of Alan Knudsen and Paul Zingersten, in the classical situation, so not in the quantum situation, these structure constants we're going to see in this talk did arrive as certain things that can be realized in integrable systems. So in some sense it's an open question how the things I'm going to talk about can be realized from this point of view as well. So let me start with a very brief introduction of what Schubert calculus is and what type of positivity I'm talking about. So Schubert calculus has a very long history. It's the Hilbert-15 problem in the famous list of problems in 1901. Hilbert asked to place rigorous foundations on on Schubert's emulative calculus. So Hermann Schubert was actually getting some huge formulas, emulative formulas, and people did not understand how he can get such huge numbers from putting some geometric conditions on geometric figures. And so that was in 1901, but we are in the 21st century, so since then things changed a little bit. Nowadays, Schubert calculus is understood as the study of the flag manifolds and various intersection rings associated with flag manifolds. So we're looking at just ordinary cohomology rings, K-theory rings, quantum intersection rings. People in this audience they're looking at elliptic, maybe quantum elliptic rings. So one of the features of Schubert calculus and all these cohomology theories, perhaps aside from elliptic so far, is that they come with a distinguished basis. So this basis is called a Schubert basis. I'm going to define it later on. But for this, once you have this basis, this additive basis, you can just multiply two basis elements and you get some structure constants. This Cij-Ks here. So we're going to be interested in understanding these Cij-Ks. And then one of the slogans of Schubert calculus is that these structure constants must satisfy some positivity property in the appropriate ring. It's going to be the ordinary cohomology, K-theory, maybe equivariant version thereof. And so in some sense, the goal of Schubert calculus is to obtain algorithms and hopefully manifest the positive formulae to calculate this structure constant Cij-K. And there are various things in the non-quantum theories, like equivariant cohomology, for example, or equivariant K-theory. There are algorithms to calculate these things based, for example, on localization formulas. But this localization formula don't quite give you positivity. Usually positivity is a result of a different phenomenon. Localization is a local phenomenon, and positivity in some sense it's a global phenomenon. So this is where the distinction arises. So in this talk, I'm going to focus mostly on the quantum K-theory of Grassmannians. But more generally, I'm going to look at quantum K-theory of any flag manifold. And this quantum K-theory of any flag manifold, again, comes with a distinguished Schubert basis. And you're going to guess these structure constants, N, U, V, W, D. They depend on U, V, W, and D, which are just elements, appropriate elements in the Y group. And there is this old conjecture, I think, is Leonardo Mihalcea, early 2000s, based on combinatorial considerations, and then Book and myself in 2008, based on geometric calculations. So we made the following conjecture that these structure constants are alternating, in the sense that these are integers, or maybe in the equivariant case they're going to be polynomials. But let's say they are integers in this case. So they are integers and they have a predictable sign. So -1 to this length of u plus length of v minus the length of w. In other words, -1 to the degree of the right hand side minus the degree of the left hand side. times the structure constant is larger than 0. So this is the degree of the right hand side minus the degree of the left hand side. So length of u plus length of v, length of w, and then the degree of this q to the v. So the difference in degree should give you a sign, and that sign multiplied by the coefficient should give you a non-negative integer. Okay, so this is the conjecture. As I said, is still wide open as far as I know in the full generality. But let me give you like a very brief overview of what positivity is and how does it arise in the cohomology theories that we're looking at. So this is a diagram of various rings and quantum rings that we're considering. So on the bottom side, you can see the ordinary rings. So you can see here the cohomology of X. X is a flag manifold, could be anything really, but for positivity, flag manifold. Here you have K theory. If you want to go from K theory to the cohomology, well, K theory is a filtered ring, and you have to take the GER, the associative gradient of the filtered ring to recover cohomology. And then you have the equivariant theories here. So you have equivariant K theory, you have equivariant cohomology. Again, this is a filtered ring, and you take the associative gradient to get the equivariant cohomology ring. If you want to go from the equivariant rings to the non-equivariant rings, you have to specialize the parameters accordingly. So the parameter goes to 0, so that means, and if you exponentiate it, you get e to the 0 goes to 1. This is this arrow here, and then in the cohomology case, it goes to 0. And then you have these elliptic theories. Elliptic theories are much more difficult for me as a person who works in Schubert calculus, because the notion of fundamental classes doesn't really exist. Fundamental classes only exist for smooth varieties. So the Schubert classes that I'm going to talk about later are not smooth. Normally you have to resolve a Schubert class, but there are many resolutions, and there is no canonical way to choose one resolution versus another. So there is a problem in elliptic cohomology for me on how you define fundamental classes. Perhaps the theory of elliptic stable envelopes is going to solve this problem, but even then there are some parameters that need to be fixed. So for me this is a bit mysterious, this part, and I think some people in this workshop, maybe on Friday, are going to talk about specializations from the elliptic side to the equivariant K theory side. Okay. And of course this is the bottom layer, and the top layer you add a Q to everything. So you have quantum cohomology, quantum K theory. You may even try to add quantum elliptic or equivariant quantum elliptic. From my point of view, these two rings are rigorously defined. For example, I'm going to give the definition, which is due to given term B. On the elliptic side, there are cobordism, Gromov-Witten invariants, which have been defined by Coates and Givendal. But I have not seen the definition of the quantum ring in that situation. So there are some things to be checked out from my point of view. All right. So as I said, we're going to consider here X to be either a flag manifold, or it could be a cotangent bundle of the flag manifold. We've seen this several times. And the story is that if you change from the tangent bundle to from the flag variety to the cotangent bundle of the flag variety, you change the Schubert basis. So essentially, you go from the fundamental classes to the stable envelopes. So I'm going to give you positivity statements, some proved, some conjectural, that hold in each of these theories. So let me just briefly introduce the main objects. So I'm going to consider for simplicity G mod B to be the complete flag manifold, so the manifold that parameterizes flags F1, F2 in Cn. So the value associated to this flag manifold is the value for G, which is just the symmetric loop in n letters. And then you can look at the B orbits and the B minus orbits, where B is a Borel subgroup. So you can think of the Borel of either the upper triangular or the lower triangular matrices. And you're looking at the orbits. I'm denoting here EW, a fixed point. There are finally many fixed points in these situations. And then a Schubert cell, respectively, or an opposite Schubert cell, are given by the B minus or the B orbits of this fixed point. So Schubert cell is just B minus times the fixed point, and the Schubert variety is the closure of that. These are honest cells. So they are isomorphic to to an affine cell which has dimension equal to the has codimension, I should say, equal to the length of W here. So these are Schubert cells. They give you in fact a stratification of flag varieties. So there are two types of cells, these B and B minus ones. And you can take the fundamental classes of the closures of these cells, and just a general theory tells you that these fundamental classes should give you a basis for whatever cohomology theory you're looking at. So in this case, let's just state it for cohomology and K-theory. So the cohomology of the flag manifold has an additive basis given by the fundamental classes of the Schubert varieties, and the K-theory of the flag variety, which I'm going to define again more precisely later, is going to have a basis given by these classes of the structure shifts of the Schubert varieties. Okay, so I want to tell you a little bit about positivity. This is a crash course in positivity for now, and then I'm going to discuss the quantum side. So what type of positivity do we get? So let's say that you in this slide everything is the complete flag manifold. I'm going to multiply two fundamental classes of the Schubert varieties. If I multiply them in cohomology, you get these structure constants, which I'm going to denote by CHUVW. So H stands for cohomology. So these are going to count points. So the structure constants is the number of points in the intersection of three Schubert varieties placed in general position. X upper U, X upper V, and the concurrent dual of the third. So you're counting points, so obviously you're going to get a non-negative answer. So from the geometric point of view, it's obvious that these structure constants must be non-negative. The question, of course, is to find a manifestly positive formula for this structure constant. In K-theory, you have an alternating positivity. So if you multiply two structure shifts of Schubert classes, and then you look at this structure constant, then again the degree on the left-hand side minus the degree of the right-hand side gives you a sign. If you put that sign in front of the structure constant, then you get a non-negative integer. So this is what is stated in this positivity. Then there are quantum versions of everything. So if I upgrade these rings to the quantum versions, quantum cohomology, quantum K-theory, I have exactly the same type of positivity. So in quantum cohomology, I'm not going to count points anymore, but I'm going to count rational curves of a specified degree. In quantum K-theory, I'm not doing the counting anymore, but it's something you'll see later on. It's like a measure of the space of curves. The space of curves that pass through three Schubert varieties could be positive dimensional, but you have to look at the other characteristic in some sense. And then there are equivariant versions of everything. So if you work with the equivariant versions, then the structure constants are no longer integers. They are structure constants in the equivariant intersection theory of the point. So you may have equivariant cohomology of a point, you may have equivariant K-theory of a point. So you have either polynomials or Laurent polynomials, and then there is the statement is that you have some positivity for these polynomials. So the polynomial can be written as a sum of simple roots with some non-negative integers, or in the K-theory it's going to be 1 minus e to the simple roots. So you can formulate a positivity for this equivariant K-theory as well, and also in the quantum situation. Alright, so this is the crash course in positivity. Any questions? I'm gonna move towards the Grassmannian and towards quantum K-theory from now on. Alright, so I'm not gonna move. I didn't tell you anything about the cotangent positivity. So this is actually a little bit more interesting, and this is very new. So as I said, in the cotangent bundle situation, a good basis is to consider the stable envelopes corresponding to Schubert, to elements of the value, because we've seen in Andrei's talk yesterday, it was related to this atrium, these attracting sets which correspond to value elements. So if you take the stable envelope, it's an element of the cotangent bundle. Well, it's an element in the equivariant cohomology or equivariant K-theory of the cotangent bundle. So I don't like to multiply in non-compact spaces. So what I'm going to do is I'm going to consider the cotangent bundle, and I'm going to consider the zero section. So this iota is the embedding of G0 B inside the cotangent bundle. If you want to think from the Quiver variety point of view, is that the cotangent bundle is a Quiver variety, but it comes with a distinguished Lagrangian cycle, which is the zero section. So I'm going to pull everything back to the zero section, and if I pull everything back to the zero section, then I'm going to get a class in the cohomology or equivariant cohomology or equivariant K-theory of the base, which is going to remember this extra parameter, this extra dilation parameter. And it turns out that if you do that for the stable envelopes, you recover the classes that have been defined earlier in relation to singularity theory. So, for example, if you do that in cohomology, if you pull back the stable envelope, and here I'm lying because you need to specify what normalizations you're using and so on. But if you use the correct normalization, then the pullback of the stable envelope recovers the so-called Chern-Schwarz-McPherson class. This was a class that was defined by McPherson in 1974, I think. So it's almost 50 years ago. Yes?
Sorry, so but here we are in the equivariant setting then?
Yeah. Everything is equivariant. You can work in the non-equivariant setting, so you can forget about the torus, but still remember the C star, the dilation. And then you're going to get, so in fact the statement that I'm making here, just for simplicity, is made in the C star equivariant cohomology. So C star acts non-trivially on the cotangent bundle, it acts trivially on the base, and it has the effect of homogenizing everything. You can go between the C star and the non-C star. These are classes which are completely equivalent to the stable envelopes. You cannot distinguish them from the point of view of localization, for example. So if you do this, and if you multiply the Poincaré dual of these Chern-Schwarz-McPherson classes, then you get some structural constants. These structural constants have a beautiful geometric interpretation. They are just the Euler characteristic, topological Euler characteristic of the intersection of three Schubert cells, in this case, in general position. So if the three Schubert cells actually intersect in dimension 0, you are recovering the usual Miriam-Richardson coefficient from cohomology. But in general, the intersection could be positive dimensional, and if that's the case, then you have to put a sign there. And this was a conjecture that was observed computationally when we started calculating these things. Knudson and Pozzi-Justin also observed this conjecture, and actually proved it for up to, I think, maybe 3-step like manifolds, using integrable systems, by the way. And the conjecture was finally proved maybe 2 months ago by Schurman, Simpson, and Wang, Bottom Wang. It says that the structural constant times this expected sign is actually non-negative. So this has been proved. You can do this. You can play the same game in K-theory. In K-theory, calculations are more complicated, but again, you get a positivity statement. So if you pull back the stable envelopes, you get some classes that have been defined much more recently, in 2001-2, by Brasselet, Schurman, and Yokura. They are called motivic Chern classes. And if you take the Poincaré dual of these motivic Chern classes, and if you multiply them out, you get some structure constants, which if you work C star equivariantly, they're going to be polynomials in this y. Y is the e to the minus h, where h is the dilation character. And then you can formulate a positivity just based on calculations. As far as I know, this is wide open. So you can formulate a positivity if you replace y by minus y, and if you put the sign, then you get a polynomial which has non-negative coefficients. So I'm not aware of any elliptic version of positivity. In fact, I was talking to some people at this conference. I don't even know how to formulate such a thing. If there are any ideas, I'm quite open. There are issues about choosing line bundles which parameterize, which correspond to elements in the equivariant elliptic homology of a point, and so on. When you multiply these things, sections of these line bundles, there is a problem. So for me, this is, for a Schubert calculus person, this is a question: is there some elliptic positivity property? All right. So any question about this?
Can you explain the meaning of Z, Y greater than 0?
Yes. This is a polynomial in Y with non-negative coefficients. Yes, the coefficients are non-negative. This is going to be a polynomial. These classes have an amazing number of properties. If you look at the coefficients and so on, in some situations they're supposed to be log concave. So there are all kinds of properties that we don't know how to explain. But we just observe them in calculations, and yeah, this just means polynomials with non-negative coefficients.
Why you take one dual?
that's how for this particular statement I want Poincaré duals. I really want the Poincaré dual of the motivic Chern classes. It's the same as in cohomology. You want the Poincaré dual of the CSN classes. So somehow the canonical classes defined in geometry are the CSN classes and motivic Chern classes. So they are the unique classes that satisfy some punctoriality property, and I want the Poincaré dual of those. That's like so the CSM and the motivic Chern classes are homology classes, and the Poincaré dual are in some sense cohomology classes. And the cohomology classes, when you multiply, are supposed to behave better, and indeed they do. Alright, so I'm moving towards quantum K theory of Grassmannians and explain what we know in that situation. So I'm going to redefine the wheel again. So now we're switching to Grassmann manifolds, which parameterize subspaces of dimension k in Cn. So as before, this is a homogeneous space under GLN, has finally many Borel orbits, and then you can look at Schubert varieties, which you can actually write down explicitly. So so this is the space of the subset of those V's will satisfy certain incident condition with respect to a fixed flag. There is also an opposite Schubert variety, so notice the x upper lambda and x lower lambdas. These are good if you want to intersect a Schubert variety, you want to intersect with an opposite one, and then the intersection is transverse. With these conventions, the dimension of x lower lambda is equal to the dimension of x upper lambda is the number of boxes in the Young diagram corresponding to lambda, and this is an example of a Young diagram here, 6, 4, 2, 1 in GR5. Well, probably this picture should be familiar to everyone here. Okay, so just rush through the definition of K theory in case you haven't seen it. So K theory is a ring which is given by symbols of vector bundles over X divided by relations coming from short exact sequences. So whenever you have a short exact sequence, 0 in F and E in G, then the symbol of E is equal to the symbol of F plus the symbol of G. So this is the Grothendieck K theory modeled on vector bundles. This is a ring. The addition is just add up the vector bundles, and the multiplication is just tensor the vector bundles. There is a pairing, which is given by, well, you give me two symbols of vector bundles, you tensor them, and you take the sheaf-Fowler characteristic. So this is a ring with a pairing. The pairing can also be thought as pushing forward to a point. And finally, if I have a closed subvariety in X, then this closed subvariety has a structure sheaf, and because X is a projective manifold here, then the structure sheaf of this closed subvariety has a finite resolution by vector bundles. So because it has a finite resolution by vector bundles, then I can think of the class of the structure sheaf as an alternating sum of vector bundles, so I can regard the class of this structure sheaf as an element in K theory. And finally, I'm just repeating what I said before for full flag manifolds, the Schubert varieties, the structures sheaves of the Schubert varieties, their fundamental classes, they give you a basis for the K theory, and this is the statement here. So the K theory, it's a free module, and there should be some Z's here, so it's a free module given by Schubert classes. Okay. Alright, so let me tell you a little bit of quantum K theory. So in some sense, this is the main object of this talk, and it was the main object of my lectures the previous week here.
Sorry, you have to say it is a small quantum theory.
Yes, it's the small quantum.
Not big.
Yes, thank you. Yes, indeed, it is the small quantum K theory. Yeah. So quantum K theory, I'm using the definition of Juventhal and YP Lee. So in this slide, up to the Grassmannian side, we can take X to be any complex projective manifold and Q to be a sequence of Novikov variables. And this sequence is indexed by a basis of H lower 2. And we're defining a degree for these quantum parameters, which is given by the Firstian class of the tangent bundle intersected with that class. These are very standard definitions. In any quantum cohomology theory comes with these definitions. And quantum K theory as a module is very easy. It's just K theory, the usual K theory, tensor product with a power series in this quantum parameters. So as a module, automatically this is a free module because K of X is a free module. It's just extending scalars. This power series is needed. You're gonna see later on. Is in principle you don't know when you multiply two Schubert classes. You don't know whether the product is finite or not. So in principle you might need the power series to express a single product. It turns out that this product is in fact finite, but that's a serious theorem. So I'm going to talk maybe later on about this. Okay, so how do you define a product? At this moment I just defined you the additive structure, but how do you define a product? You define a product by defining the pairing and imposing the Frobenius property. So I want to define a pairing which deforms the usual intersection pairing. So this, let me just pick two elements, A and B, in the in K of X, because I'm going to extend this pairing by linearity, by 0 to linearity. And the pairing of A and B is obtained by the usual pairing, so this is the classical part, and then here you have with blue the quantum part. So this A, B, comma, D are 2-point Gromov-Witten invariants, which I'm going to define on the next slide. But at this moment, just think of these as numbers. So they depend on this degree D. And then the product is, so this pairing is going to be non-degenerate, and the product is obtained as the unique product that satisfies this property. So if I want to specify what is the product of A times B, then I pair that with C, and I impose the condition that A times B paired with C is the sum of all 3-point invariants A, B, C of all possible degrees D. Again, unlike in quantum cohomology, this sum here could be infinite, and in fact very often it is. Okay, so if you unravel this is a bit complicated, but if you unravel this, then you get to this recursive formula. So the 3-point structure constant coming from the multiplication of two Schubert classes is obtained by taking the 3-point invariant, so for lambda mu and the Poincaré dual of this mu, so this dual here means Poincaré dual, and then you have to subtract some 2-point Gromov-Witten invariants and some structure constants for strictly smaller degrees. So you see, this is kind of hard to absorb. So this is recursive because the degree D here is strictly less than the degree D there. But the definition, a single structure constant, depends on knowledge of 3-point invariant and of 2-point invariant. So it's quite a complicated thing, and it's unclear, as I said, if you take D very large, why would this be equal to 0, for example? So my next goal is to tell you how you calculate these things for Grassmannians. So I will tell you how you calculate 2-point invariants and how you calculate 3-point invariants of this shape. Okay, so let me tell you about. Well, before I do that, let me make the conjecture. So the positivity, which is now a theorem. So this theorem was proved by Anders Buch, Leonardo Mihalcea, myself, and Nicolas Perrin last year. It says that if you multiply two Schubert structure constants in the quantum K theory of the Grassmannians, and if you look at these structure constants, then indeed you get that this positivity that was conjectured holds for Grassmannians. So this positivity generalizes other positivity properties. So for D is equal to 0, generalizes a positivity that was proved by Buch, combinatorial, just for Grassmannians, and by Briand for any G mod P. So the underlying reason for this, I'll see if I can get to talk about that. The underlying reason is cohomology vanishing and some rational connectedness properties. Let me explain, maybe it's going to be a bit geometric, but let me explain how do you see the positivity in a very simple example in the classical case. So this is Briand's example. And, well, okay. Let me pass over this. So this is one example. This is one example of what the positivity says. So maybe I'll explain the conjecture in one example. So this is O 3 to 1. So the degree of this thing is 6 plus 3 is 9. So I'm looking at the degrees of the right hand side here. And whenever I see a degree which is more than 9, I subtract that degree from 9. So this has the degree 3 plus 3 plus 3, it's exactly 9, it comes with plus. This has degree 9 again, because degree of Q, this is an example in GR26, GR36, I'm sorry, GR36. And here the degree of Q is 6. So 6 plus 3 is equal to 9. So there is a plus sign here. Here again, 6 plus 3 is equal to 9. 6 plus 3 is 9. 6 plus 4 is 10. 10 minus 9 is 1. So if you see a negative sign, you also see a coefficient of 2. But the point here in the positivity is that negative sign. There is, here it's 6 plus 5, it's 11. 11 minus 9 is 2. So you see a plus sign. 6 plus 6, this is 6 plus 6 is 12. 12 minus 9 is 3. You see a minus sign. So that's the positivity in a particular example. This was obtained using the formulas I'm about to present and using software by Anders book, which is available publicly on the. You can also see here, if you just look at the terms of degree 9, you will recover the quantum cohomology multiplication. So the quantum cohomology multiplication of that class times this class goes up to here, because up to here everything is of degree 9. So these black terms and these teal terms. Everything else is like a quantum K correction beyond this. Alright, any questions about this particular statement? Is it clear what positivity means in this example? Okay, I'm assuming it is. I promised you a special case of the positivity just to see it in action. Like how do you prove such a thing just for the non-quantum case, for the classical case? So let's say we're looking at a smooth subvariety of Pn. Could be a curve, could be hypersurface, smooth. Smooth is important. And then you calculate, you want to expand this subvariety. If you believe what I said before, this says that the structure shift of this subvariety has an expansion in terms of the structure shift of the Schubert basis. The Schubert basis for the K-theory of Pn consists of structure shifts of lower projective spaces. So this p to the I is where I go from 0 to n. So you're interested in this coefficient here, ai. How do you calculate these coefficients? Remember, K-theory is a ring with basis. So you calculate the coefficients by pairing the class of y with the class of the dual of this pi. I'm telling you that the class of the dual, so this Poincare dual of the pi, is obtained in fact as the class of the opposite kind of complementary projective space. So from pi go to Pn minus I, but you also have to multiply by this twisted self shift of -1. So I have to calculate the Schiff-Euler characteristic of this triple product. But when you, because y is general, I mean, because I can transfer everything into general position, then the product of this OY with OPn minus I is just O of y intersected with Pn minus I. So this is actually absorbed into this term, and then O of minus 1 remains. So I have to calculate the Schiff-Euler characteristic of this y intersected with this general linear space with coefficients in O of minus 1. So okay, this is a null characteristic, and now I use the famous Kodaira vanishing theorem. So the Kodaira vanishing theorem tells you that all the lower terms are 0. O of 1 is an ample line bundle, O of minus 1 is the inverse of an ample line bundle. So when you take the cohomology of a smooth variety with respect to an inverse of an ample line bundle, all the lower cohomology is 0, and only the top cohomology survives. But the top cohomology has exactly the sign that you want. So the top cohomology has this sign, and this is the sign that is predicted by positivity. So that's how you get positivity in the classical case. In some sense, you get positivity in the quantum case in this way also, but things are much more complicated in the sense that you have to perform certain push forwards, which are very complicated geometrically. So, all right. So Brion in fact had a more general positivity that says that if you have a variety of rational singularities and if you expand that into Schubert classes, then this coefficient satisfy positivity. Okay, so let me move towards telling you what the two-point Gromov-Witten invariants are. So let me recall the formula. This was the formula for the structure constants. so which depended on 3-point invariance and 2-point invariance and something that was recursively defined. So I have to, so now I'm going to spend some time telling you what these things are, the 2-point invariance. Alright, so what are the 2-point invariants? First of all, I have to define some spaces here. So I'm going to look at the moduli space of stable maps of degree d to x. This is a particular moduli space that compactifies curves from P1 with n mark points into x of degree d. I'm not going to define carefully this space. I'm just going to say that it exists. It has nice singularities, almost smooth essentially, and it comes equipped with evaluation maps. So you can evaluate a curve at each of these n mark points, and you have these evaluation maps EVIs. And then what you do with these evaluation maps, you're going to pull back cycles from x, and you're going to intersect in the moduli space, and you're going to take all the characteristics. So for example, if you take n classes in the K theory of x, then the n-point Gromov-Witten invariant of degree d is obtained by, as the other characteristic over this moduli space. You pull back the first class, the second class, you multiply them out inside the K theory of the moduli space, and then you integrate, you take the other characteristics. So that's the definition of the K-point, of the n-point Gromov-Witten invariant. And then there's also the Gromov-Witten variety, where you don't integrate, you just kind of pull back the classes and you look at the scheme of those maps, which are incident to the cycles, omega 1, omega 2, omega 3. So this is called the Gromov-Witten variety. And there are various boundary versions of this, which are actually important later on for the proof of positivity, where the general map has a particular splitting. So for example, you may have a map of degree d comma 1, where you have like some curve of degree d, and then a component corresponding to some curve of degree 1. So you might have like a crossing thing. So a general element in that space would be some kind of like singular curve. Okay, so then we can define curve neighborhoods. Curve neighborhood, they have a beautiful construction. It's just an incidence thing. So you take the moduli space of stable maps with 2 mark points, and then you pick a subvariety omega in x, and then you just pull back, push forward. So pull back, push forward. So this is called the curve neighborhood of omega. And if you think what it is the locus of curves inside the flag variety which intersect omega. So it's the locus of curves of degree d which intersect omega. That is the curve neighborhood, and they have unexpectedly good properties. The first property it's that if you start with a Schubert variety, the curve neighborhood is again a Schubert variety. Why would this be true? This is because the Schubert variety is irreducible and stable under the Borel group, and the curve neighborhood also happens to be stable under the Borel group, and we have to prove irreducibility. And then once you believe that the curve neighborhood of a Schubert variety is again a Schubert variety, there's a super easy formula to calculate 2-point invariants. In fact, for any flag manifold. So if you want to pair the class of a Schubert variety with the class of the Poincaré dual of a Schubert variety, these are the 2-point invariants that appear in the formula. It's always 0 or 1. This is always 0 or 1. It's 1 exactly when the relevant curve neighborhood of x upper u is equal to this xv, and it's 0 otherwise. And furthermore, if you may ask, okay, how do I calculate these curve neighborhoods? There is a recursive formula, and for Grassmannians, the recursive formula is actually quite recursive in the sense it's only enough to calculate curve neighborhood of lines. So for Grassmannians, if you're looking at curves of degree d, you just look at gamma 1 of gamma 1 of gamma 1 of gamma 1 d times, and you're going to get the curve neighborhood of degree d of omega. Let me give you an example. So this is the example. Perhaps a picture is worth 1,000 words. So what's the example here? It says the following. So if I'm interested in the curve neighborhood of x upper lambdas, or the curve neighborhood of x lower lambdas, so this should be Schubert varieties consisting of curves that intersect x upper lambda, respectively x lower lambda. So because of the conventions, I expect the dimension of the curve neighborhood always grows. So that means codimension decreases. So gamma d of x upper lambda is obtained by you take lambda and you remove d maximal ring hooks. And if you take gamma d of x lower lambda, you add d maximal ring hooks. So here is an example where I'm adding d maximal ring hooks. So the partition here is 3 to 1. So the two maximum ring roots are these ones and that one. So in this case, the gamma d of 3 to 1 is this 7, 7, 5, 4, 3. So you can really write down what these things are. That's what I'm trying to convey here. It's really combinatorial by now. So this gives you a formula for 2-point chromo-Witten invariance. Such a formula is actually available for any flag manifolds, but it's a bit more complicated. When I give this talk about quantum K theory, I always have to say something about this unexpected thing. So this is a statement about quantum K theory that was proved just by knowing what the 2-point invariants are. It says the following. So let's look at the quantum order characteristic. So you take chi from the quantum K theory to just quantum K theory of a point, and then let's assume that I work over the polynomial version. So I don't have like power series, and I'm specializing Q to 1. So this is why I need to work over the polynomial version of the quantum K. And then the statement is that this quantized version of the order characteristic, where you specialize all the Q's to 1, is in fact a ring homomorphism. This is completely unexpected, and it's also completely false in any other cohomology theory. Quantum K theory is the first theory where such a ring homomorphism is true. So in fact, you may think of this order characteristic as the push forward to a point. So you go from G mod P to G mod G. Well, Kato says that you don't have to go from G mod P to G mod G. You can go to actually from G mod B to G mod P, and you put quantum K here, and you just push forward, and you make some of the quantum parameters equal to 1, and he proved this amazing result that this projection, which makes some of the quantum parameters equal to 1, is always a ring homomorphism. Now, the theorem, which is with Wu, Chang, myself, and Chang Zheng Li, is not hard to prove, but this is a very deep theorem, this theorem of Kato. So I just want to emphasize this. In some sense, if you're not interested in quantum K theory, this should give you pause and think this is the first theory where something like that occurs. That this push forward is actually a ring homomorphism. As someone training, like studying intersection rings, push forwards are never ring homomorphisms, but it is in this case. Alright, so how do we calculate 3-point invariance? So the previous theorem only required, in fact I didn't give you the proof, but it only required knowledge of 2-point invariance. That's enough if you want to get that statement. But 3-point invariants are more delicate. So this is the quantum equal classical statement that says the following. So let's say that I'm interested in calculating a 3-point chromo-Witten invariant on the Grassmannian. Then I'm going to do this incidence variety. So I'm going to fix a 3-point invariant, so 3 classes, and I'm going to fix a degree D for my curves. And then I'm going to do this incidence variety, so I'm going to have a 3-step flag manifold, this one, and a 2-step flag manifold, this one. And then the statement is that, okay, well, pick 3 classes A, B, C, and I want to calculate this 3-point chromo-Witten invariant, A, B, C. So just take A here, so the A is in the K theory of this, pull it back, push it forward. Take B, pull it back, push it forward. Take C, pull it back, push it forward. So the 3-point chromo-Witten invariant, which is to be calculated on the Grassmannian, is equal to a classical invariant, which is calculated on this 2-step flag manifold. So this is why this is called quantum equal classical. So these calculations, as I explained very early in my talk, there are all kinds of methods to deal with these classical calculations. So there are programs and so on. So in principle, using this formula, you can calculate any 3-point invariant you want on the Grassmannian. Why is this true? This actually goes back to an observation, a beautiful lemma by Anders' book, which says the following thing. So if you take a rational curve of degree D to the Grassmannian, then you can look at the images of the elements in P1. Well, the images are just subspaces of dimension K inside Cn. So you have a bunch of subspaces which are indexed by this P1. So you intersect all of them, or you take the span of all of them. So if you intersect all of them, you're intersecting infinitely many subspaces, so you expect that you're going to get something which is 0-dimensional. infinitely many subspaces. But in fact, that is false. You get something which is actually well behaved. So the dimension of this intersection, which is called the kernel of the rational curve, is always larger or equal than k minus d. So it's not too small, and the dimension of the span is not too big. And furthermore, for a general curve, these inequalities actually are equalities. So the k minus d and k plus d are precisely those that come up here. So essentially, this variety YD is the collection of kernels and spans of the rational curves that pass through the cycles A, B, C. This is how you think about this. This type of statement has a long history. It started with the book Kreshn Pavlakis in quantum cohomology, and we did it in equivariant cohomology, K theory, and equivariant K theory. And I should say in quantum cohomology, they really counted curves. So they really proved this statement by counting the curves on the left and pairs of kernel spans on the right. But you cannot do this in equivariant cohomology or in K theory. You don't count, because there is no counting anymore. So we had to use a completely different proof. There is a version that allows you to go from the Grassmannian to the Grassmannian, but I'm going to skip over it. Just to give you a laundry list of applications. So this quantum equal classical theorem has many applications. For example, you can get structure theorems. When you multiply by Thierry classes or Chevalier classes, you can prove positivity. You can find presentation of the quantum K-ring as a ring presented by generators and relations. And finally, we are using this quantum equal classical to prove positivity. So what's the idea beyond positivity? I know I'm getting close to the end of my allotted time. So let me give you in one slide. Really, this is one slide where everything occurs. Although this one slide is like 60 pages of paper, so it encodes many things. So how do you prove positivity? So you're interested in calculating the product of O lambda by O mu. For reasons that have to do with transversality, I want opposite classes, O lower lambda and O upper. I'm interested in a particular structure constant, but that's the same thing as like actually pushing forward a class and expanding into Schubert classes. So what classes am I pushing forward? So I'm pushing forward the classes of the Gromov-Witten variety of curves that intersect x lower lambda and x upper mu. And I'm also pushing forward the classes of curves with reducible domains, so something of this form. So this is like b minus 1 and 1. And then you have like 2 points here and then a point here. So you have like curves with reducible domains. So this is a particular Gromov-Witten variety inside the moduli space. I have to push forward that one. That one is a divisor inside the field. So I need to calculate these push forwards. Usually calculating push forwards in K theory is a complicated thing if the map is not birational. And in fact the map is not birational. The maps are not birational here. So okay, so I need to calculate these two things. It turns out that the first calculation is not too hard. It's interesting but not too hard. So the first calculation recovers dispositories that were defined by Knudsen, Mann, and Speyer. So you have that the push forward of this Gromov-Witten variety is this O gamma d lambda nu. So this is the locus of the space of maps of degree d that intersect these two opposite Schubert varieties lambda and nu. That exactly coincides with this with a particular projected Richardson variety that has been studied by these authors. So in particular, we know it has the correct singularities. We know that the push forward behaves as expected. So this was fine. So by Bion's theorem, once you know this, then you can expand that into Schubert classes, and you get that this class has the required positivity probability. Why this paper is complicated is because of this. So we still have trouble, in fact, completely understanding this push forward. So we kind of like got enough to get the positivity. But there are still unknowns about this push forward. So what can happen? So what can happen is that this class is equal to that class, and that's what you expect for large degree. So for large degree, we prove that the first class is equal to the second class, therefore the class is 0, so positivity holds automatically, there's nothing to do. However, for small degrees, you have to work. So for small degrees, we can actually prove that this Gromov-Witten variety is a divisor inside the bigger one, and also the image is either a divisor or is equal to this projected Richardson variety. So we have to analyze both situations, and we actually have to perform the push forward. So this is proving these facts here about cohomology vanishing is the bulk of the paper. We have to develop the technology that proves these push forwards. And then once you prove this, you show that either the structure constant is 0 or you have two classes with opposite alternation. And then if they have opposite alternation, when you subtract that, they have correct global alternation. And so I'm essentially out of time. Let me just tell you the conclusions. So we calculated the 2-point invariance, and then therefore the quantum K pairing. We also calculated the 3-point invariance. We used some geometry to get to these positivity statements. And I have many questions. In particular, I have no idea how to prove such a thing in general. There are some particular situations by Leonardo, Naito-san, Sagaki-san, where they multiply a Schubert class by line bundles or by certain Schubert divisors where the positivity occurs. But these are special cases. We don't know what happens in general. We want to know, for example, how to clarify connections between given Talon-Lee quantum K theory that I'm calculating here to other quantum K theory. For example, quasi-map quantum K theory, perhaps quantum K theory with level. So we don't know how to calculate here. And finally, I promised I'm going to mention integrable systems. This is it. So I want to clarify the connections to integrable systems. And I don't want to make it as an afterthought. Actually, I regard this as a very important problem. So certain structures that arise in the geometric quantum K theory do fit with certain multiplications with operators in quantum K theory. But writing a dictionary between the integrable system and geometry is absolutely non-trivial. And I am personally working on partially on that story, so I'm quite interested in that problem. So I'll stop here. Thank you.